Welcome back. In this lesson, we're diving into periodic trends, the patterns that explain why elements behave the way they do. By the end, you'll know how atomic radius, ionization energy, electron affinity, electronegativity, ionic radius, metallic versus nonmetallic character change across the table, and the important exceptions that make chemistry so interesting. Note that all trends below are for s and p block electrons. Transitional elements do not follow a regular predictable change. So let's begin. Atomic radius is the distance from the nucleus to the outermost electrons. So this will be the diameter. Because electrons are negatively charged, they are attracted to the nucleus, which is positively charged. In a mini-electron atom, each electron is simultaneously attracted to the nucleus and repelled by the other electrons. Your teacher may call the repulsion of inner shell electrons as being shielded or screened. Therefore, we can use the term effective nuclear charge when describing the attractive forces between the nucleus and the outer shell electrons. Also note that the bonding radius is shorter than the non-bonding ionic radius. So essentially, these inner electrons are repelling the outer electrons, causing it to become large. The more electrons that I put in the outer shell, the shielding effect does not increase. So therefore, the electrons are pulled more tightly in towards the nucleus. The trend is, if I'm going downward, the atomic radius increases because I have additional shells. If I go across, we decrease in size because the effective nuclear charge is increasing, pulling the electrons closer in. So it increases going down, decreases goes to the right. Now, usually we do not include the noble gases here, because noble gases don't usually form, but the trend still holds true. The ionization energy is the energy needed to remove a ground state electron from the gaseous state of an atom or ion. Note that the ionization energy is usually positive because energy is being added to the system. An example will be something like sodium gaseous plus energy will produce a positive sodium ion, again gaseous, plus an electron. If this change in energy is like 496 kilojoules per mole, this is an endothermic reaction because I have to add energy to cause it to remove the electron. The trend is, if I go in this direction, if I go downward, the ionization energy decreases. And the reason that it decreases is because the outer shell electrons are further from the nucleus. If I go to the right, the ionization energy increases because the radius is becoming smaller. Because the nucleus is pulling harder on the outer shell electrons. Between groups 2 and 13, boron has a lower ionization energy than beryllium. Okay, so let's highlight those here. Okay, so we have beryllium here and boron's here. So boron has a lower ionization energy than beryllium because removing an electron from boron's 2p orbital is easier than from beryllium's stable 2s2 orbital. oxygen has a lower ionization energy than nitrogen. And the reason why is nitrogen has a half-filled 2p Nitrogen has a half-filled 2p configuration, which is extra stable, while oxygen has just one pair of electrons. So for oxygen, we would have by having this one pair here, oxygen is easier to remove an electron. So to summarize, we can say then that half-filled subshells like P3 or P6 provide extra stability, explaining why we have dips in our transition. Electron affinity is the energy change when a gaseous atom gains an electron. For most atoms, energy is released when an electron is added, and the energy will be negative because the energy is released. So a good example would be, let's say, Cl as a gas plus an electron. It'll produce Cl negative as a gas, and the change in energy be negative 349 kilojoules per mole. So this is an exothermic reaction. The trend is if I go across from left to right, it becomes more negative. If I go down, it becomes less negative or decreases. Since the extra electron will be further from the nucleus. So notable exceptions, groups 2 and 18. So here's 2 and here's 18 over here. Adding an electron will force it into a higher energy orbital. So their affinities are near zero or even positive. Nitrogen here is lower than expected because of its stable half-filled P3. Fluorine, another oddity, has a lower value than chlorine. Even though fluorine is more electronegative, it's very small in size, means adding another electron causes strong repulsions in its compact 2p orbitals, so chlorine actually has the highest electron affinity. So some teachers will actually test you on this, so be careful there. Electronegativity is the ability of an atom or molecule to attract shared electrons to itself. This is going to increase going from left to right, decrease going downward. Noble gases here are usually not included because they rarely form any bonds. Understanding electronegativity will help you predict bond types. So if I have a bond between something on the left side and something on the right side, what I want to do is I want to subtract the electronegativity. So if I subtract the difference will tell me what type of bond it will form, most likely. The larger the value, when I subtract these two values, the more likely or more ionic character it will have. If there's very little value, then I know it's going to be a covalent bond. The size of this difference will determine if it's going to be polar or nonpolar. So electronegativity is very important to understand. Ionic radius also has a trend. The ionic radius is the size of an ion compared to its neutral atom. Cations will always be smaller than its neutral atom because electrons are lost, so the remaining electrons are pulled more tightly or closer to the nucleus. So, for example, a positive ion, a cation, will be much smaller than the neutral atom it was derived from, because the remaining electrons are pulled more closely inward. The more positive it is, for example, if it's a positive 1, but if it's a positive 2 or positive 3, it gets smaller and smaller and smaller because the remaining electrons are pulled so tightly. Anions are larger because when I add an additional electrons, the electron repulsion increases, causing it to be larger. Again, so if I have a neutral atom, if it is negatively charged, it's going to be larger. So if it's 1 negative or 2 negative, it's going to be even larger because the repulsive forces increase. So across a period, cation radius decreases. So cations get smaller as I go this direction. Because the more positive they become. Anions become larger. So here, the anions become larger. If I go downward, again, they will increase in size. Metallic character describes how easily an atom loses electrons. So metallic character increases as I move left and down. Nonmetallic character is a tendency to gain electrons. Okay, so for nonmetallic, it's going to increase in this direction. And again, it will decrease going downward. The most nonmetallic element on the periodic table will be fluorine. Okay, let's see if we can predict which is the smallest to the largest. So we have phosphorus, sulfur, arsenic, and selenium. I have them highlighted here for you. The smallest one will be the one that's the furthest up and furthest to the right. So that would have to be sulfur. So we can say that sulfur is smaller than the next one up and over, phosphorus, smaller than selenium, and which is smaller than arsenic. In this example, we want to arrange the following in order of decreasing size. Notice I have some ions here, and I have a neutral. I know that my neutral atom is going to be much larger. So I can say the calcium then is greater in size. Now I have to pick between the other two. All right. Notice now that magnesium is here and calcium is here. So calcium is larger because it's further down. So I know then that the calcium ion will be larger than the magnesium ion. Okay, here's a new term. Arrange the following isoelectric series in order of decreasing size. Isoelectric means they all have the same number of electrons. Potassium normally has 19 electrons. If it loses one, it will have 18 electrons. Chlorine normally has 17, so if it gains one, it will have 18. Calcium has 20. So if calcium loses 2 electrons, it will have 18. And sulfur has 16. If it were to gain 2, it would have 18. So this isoelectric means that they all have the same number of electrons. Now, let's arrange these in order of decreasing size. Okay, since they all have 18 electrons, sulfur here has a -2 charge. So I know it's going to be the largest. So sulfur, 2 negative, is going to be larger than chlorine, which is also negative, because those two are larger than their neutral atoms. All right. Potassium would be next in line, and the smallest of all of these then will be calcium 2+. This lost 2 electrons. So remember, the more positive it is, the smaller it becomes. The more negative, the larger it is. Okay, arrange the following in order of increasing first ionization energy. Remember, ionization energy increases this way. Decreases this way. So if I want to arrange these in order of increasing, I need to pick the one which is the lowest. Potassium here is the furthest to the left and down. So I know that potassium then is going to be less than. Okay, let's find another one that's on the left side. There's sodium. So it can be less than sodium. Now, on this next one here, we have phosphorus, argon, and neon. So phosphorus is the furthest to the left. Argon is further down. So neon will be the highest ionization energy. So if I have barium, zinc, sulfur, and silicon, which element has the highest electronegativity? So electronegativity increases to the right, increases going up. So that would have to be sulfur. Which element has the most metallic character? Metallic character increases to the left and downward. So that would have to be barium. Which element has the largest electron affinity? Electron affinity increases to the right and up. So that would have to be sulfur. So here's the big idea. Periodic trends are all about the tug of war between nuclear charge and shielding. When you understand that, the patterns across the table make perfect sense. And the exceptions are where orbital stability and electron repulsion come into play. If you find this helpful, please be sure to like and subscribe for more chemistry lessons. Thank you for watching. Goodbye.